Good morning, everyone, and welcome to today's webinar on Hipot Testing 102. This is the continuation of our Hipot testing webinars. Of course, the last one was Hipot 101, presented by Nick Petrowski, and this is the second part to it. I'm your host, Syed Abidi, also one of the applications engineer here, and I'm here live from Lake Forest. Temperature here is 66 degrees Fahrenheit. Also joining us today on the board are Bishan Patel, who's our other applications engineer. He's the panelist for this webinar, and he will be assisting you with any questions that you may have during the webinar and that you can post on the chat line. And lastly, we have Alison Oba, who's, as you can see from the picture, very excited to be the organizer of our webinar. So she will be helping us, setting up the webinar and taking any questions or dealing with issues with audio and video. So just a quick note on some help on the webinar. As always, please feel free to use the Q&A utility to ask us any questions concerning the material being presented. Also, any questions relating to running of the meeting, audio, visual, etc., can be addressed to our host, Jim Kennedy, or in this case, it's Alison Oba. The webinar is being recorded as always and will be available to view usually within a day on our website. And if you have any questions on the presentation, or if you would like to obtain a copy of this presentation, feel free to email our, one of our other organizers, Jim Kennedy, and the email address for that is jimk@asresearch.com. Okay, once again, I welcome you all, and thank you for joining us on this very important webinar. But before we dive into today's webinar, let's quickly just go over what was covered during the previous part of this webinar, which was Hipot Testing 101. Well, during that webinar, we started by understanding the Hipot test. We tried to understand what is actually tested, some of the Hipot test requirements, such as the AC versus DC, some test parameters, and some other test requirements, failure settings, and etc. Also, some Hipot test considerations and failures, such as leakage current, dielectric breakdown, arc detection. And in today's webinar, which is Hipot Testing 102, here are our learning objectives, and hopefully at the end of this webinar, all of you, the goal is to basically make sure that all of us understand the following. We're going to start with the leakage current. We're trying to understand what leakage current means and how you can determine leakage current limits for your Hipot test. We're then going to dive into 500 VA testing, which is a special application of Hipot testing, and we're going to learn some important, other important factors concerning the 500 VA testing, such as line load regulations and when is 500 VA testing required and necessary. Then we're going to dive into some fault detections. We're going to talk about different types of failure detections and different types of instrument failure detectors that are available on most Associated Research Hipot testers. And then we're gonna come back to arc detection. I know Nick covered arc detection in quite a bit of detail last time, but we still saw some questions, so I thought it'd be a good good thing to include arc detection again to do a kind of quick review on this topic, as it's not a very easily understood topic. And lastly, we're going to talk about some safety features and functional features, and this is very important because I've had customers and people using our instruments who were not even aware of some of the safety features and functional features that were available to their Hipot test instrument. So it is very important that you know what you have available and how you can utilize those features, safety features and functional features. Okay, so that was a quick overview of what we're going to be covering today. And also, we're going to be doing some polls during our webinar as usual, and we'd really appreciate if you guys participate in those. And I have some videos for you guys as well, showing some of those failures that we're going to be talking about. So I guess we're ready to dive into the main material, which is we're going to start by understanding leakage current. However, just a quick overview of what the Hipot test is. I know most of you, a lot of you probably joined us last month, for our last webinar, Hipot 101. Actually, it was this month. And for those who didn't join us, the webinar was recorded and it's been archived on our website, so feel free to go take a look at that. But for a quick overview on Hipot test, what was Hipot test all about? Basically, Hipot test is a high voltage test. It's the application of high voltage, and the purpose is to stress the insulation of your product or your DUT, device under test, and to see how good the insulation is. We're basically testing the integrity of the insulation. So for a basic, product with a line cord, three-prong line cord, a class 1 product, the high voltage is usually applied between the current carrying conductors and the non-current carrying conductors, meaning that the high voltage is applied by shorting the mains input of your device, line and neutral, and the return is measured on either a good chassis point or on the grounding circuit to see how much leakage current is going to flow as a result of the application of that high voltage. And the assumption here is that if the insulation of a product can withstand the high voltage being applied to it without breaking down, we can assume that the product during its life cycle, the insulation will hold together and protect the user from getting shocked. So that was a quick overview of the Hipot test, what the Hipot test is. Next, leakage current. Well, all electronic products have leakage current to some extent. Some devices have leakage current values that are very small and hard to detect, but some others have higher leakage. And this leakage current is a result of the product running at its normal input voltage. Therefore, looking at this picture on the left side, we have a screenshot of our Omnia 2 analyzer, which is an all-in-one analyzer capable of also performing dielectric withstand tests. And right now what we're showing you is the AC withstand, the AC Hipot test. On the right, we're just trying to show you a simulation of a basic DUT, basically, which can be represented by a capacitor and a resistor in parallel. And the types of current, there's actually 3 types of leakage current that are possible. One is the total current, which basically is the sum of the capacitive current and the resistive current. Capacitive current being the current due to the capacitive element in your DUT, and the real current or resistive current, the result of resistance or resistance in your DUT. And the total current is the sum of the two. On the left, again, looking at the screen of the Hipot tester, you can see that a AC withstand test of 1.24 kV is set to run, and the total current is being displayed by the big meter, but on the small meter on the right side of the screen, you can see there's a real current measurement as well. And if you notice, once the test starts, the total current displays up to 2.56 milliamps, whereas the real current is just a small fraction of it, which is 0.78 milliamps. And this is usually the case. The real current is much smaller than the reactive current due to the capacitor in your device. And the reason why we're showing or simulating a DUT as a capacitor and a mix of capacitor and resistor is that if you think about how a Hipot test is performed, basically when you apply a high potential between your current carrying and non-current carrying conductors, what you're doing is essentially you're creating a big capacitor, because your current carrying conductors and your non-current carrying conductors are separated by the dielectric, which is the insulation of the product. Therefore, when you apply the high voltage, you're basically charging up the device and creating a big capacitor. Now there's got to be some resistive element to it. Therefore, we see the real part of the current, and due to the capacitance of your product, you see the reactive current. Most Hipot testers manufactured by Associated Research are capable of distinguishing between total and the real current. So that's a great feature to have for those who are trying to, differentiate and distinguish between total current and real currents. So basically, once again, leakage current is the stray current that actually flows through the insulation. It is the undesired current that we want to quantify to better understand the quality of our product's insulation. And that's the reason why we perform the Hipot test, is to stress the insulation and see how good the insulation is and how much voltage can it withstand before breaking down. Okay. Next, now that we know what leakage current is and the types of different types of leakage currents, how do we set leakage current limits? Now, all of the Associated Research Hipot testers have what we call leakage current threshold or failure limits or settings. Well, there's four simple steps to determine how to set your current high limits and your current low limits, starting with perform and record, calculate, add, and then subtract. What that really means is that if you are not sure of what to set for your high and low limits, this is basically what we recommend, and this is purely based on experience that we've had with Hipot testing, that we've come up with this rule or this method of determining current high and low limits, high and low limit current settings, failure settings for your Hipot test. So the first step is to perform a Hipot test. Take some known good products that you know are good and have passed all the safety tests in the past. Take those products and perform a Hipot test on all those samples and record all the results. Next, calculate the average leakage current value for these products. Well, when you have a bunch of sample results, you can obviously calculate the average. Then you take 25% of this number and add to the average value. This basically would be your high limit setting for the Hipot test. For the low limit, what you do is you use the same 25% and subtract from the average value, and that would be your low limit. Now remember that most standards usually call out for looking at breakdowns during Hipot tests. Some standards do specify exact values of current high limits that you need to set in your Hipot test to ensure the product does not fail. However, most standards do not give a specific value of current. All they care about is the insulation doesn't break down. High and low limits usually come as an internal requirement when some companies, especially medical, they require their basically failure threshold is much more tighter. So their high and low limits are much tighter. So they may be using 10% instead of the 25% that we recommend. Now, again, the 25% number is purely based on experience. We've been out in the field, tested, all different types of DUTs that are out there, and based on those experiences and, testing and measurements, data analysis, we've come up with this number, this method. But of course, this is not a rule of thumb. It's not called out by the standards. It's just to help you better, help you decide on how to set your high and low limits for the Hipot test. So for doing a real world example based on the method that we just talked about, say that we have 10 DUTs and we calculate an average leakage current of 5.5 milliamps. So how would I set my limits? My high limit would be 5.5 milliamps times 0.25, which is basically 25% of 5.5, and the result that we get, we just add it to the 5.5 milliamps. So in this case, 6.88 milliamps would be our high limit, and our low limit would be basically we're just going to subtract that number from our 5.5 milliamp average value, and 4.13 milliamps would be our low limit. These limits will determine how our Hipot test is going to fail. Now, when you actually run production testing and you have these your high and low limits set, your Hipot tests will fail based on these limits. If the limit is lower than the low limit, then there's obviously something wrong. Something's not connected properly, because you should see at least that much current. And if it's exceeding the high limit, then you know something is not right with the product's insulation, and it's leaking more current than your high limit. And you need to go back and look at the insulation, or look at the design or whatever, and improve upon the product. So high and low limits are very important for those who are trying to, who are very strict with their leakage current limits. Okay, so before we go any further, a quick video that I have for you guys showing the high limit, basically high limit failure. And what we're doing here is we have a capacitor connected to our Hipot tester. Our Hipot tester, as you can see, run this real quick again. It's a short video. So we have a 5,000 volts AC Hipot test with a high limit of 50 milliamps. When we perform the test, as you will see, the test fails instantly and gives you a high limit total failure message. And I'm just going to pause it here. So as you can see, the failure occurred. The voltage did not even go up to 5,000 volts, but because we had a high limit of 50 milliamps set, which is basically the max for this instrument, the instrument comes up with an instant failure saying that the high limit total was exceeded. So that's an example of how your high limit works during your Hipot test and how it can come up with a failure. Okay, next, a very important topic, a special application of Hipot tests, which what we call the 500 VA Hipot testing. Now, VA rating basically is the power output rating of the Hipot tester itself. Certain standards require the use of a 500 VA Hipot transformer. Energy and breakdown. Originally, this was required to ensure that the Hipot output, voltage output remained constant under varying line and load conditions. Well, a Hipot capable of producing 500 VA should provide enough output power to test a device under a loaded condition without allowing the output voltage to fall below the specified setting. This means that the applications most commonly requiring a Hipot with a 500 VA rating are those in which an AC voltage must be applied to a highly capacitive load. That means applying an AC voltage to a capacitive device or a product causes a flow of capacitive leakage current, which can have a dramatic effect on the total leakage, as we saw, the different types of leakage. Total is a result, this being the sum of real and capacitive current. So the capacitive leakage current is often, as we saw, much higher than the current that flows due to the resistive leakage, and in itself could cause the need for a 500 VA, 500 VA Hipot tester. However, it's usually the standards that call out if a high 500 VA Hipot tester is required. Higher milliamp output may also be required for higher leakage currents. For example, you may be testing a product that's highly capacitive and may require a Hipot tester that is capable of measuring up to 60 milliamps of leakage. Well, in this case, a 500 VA transformer or a 500 VA Hipot tester would be the right choice, because your device's leakage current is pretty high. So you want to make sure you have a Hipot tester that is capable of measuring that high of a leakage current, which usually are your 500 VA transformers or Hipot testers. Now, most associated research instruments have a 5,000 volts output, and the instruments have a 100 milliamp trip current rating and 200 milliamp short circuit current rating, which is also a requirement sometimes by the standards. Associated Research has a few 500 VA models as well, and we'll show you in one of the upcoming videos how those can be used to perform a 500 VA Hipot test. But here's the 500 VA Hipot testing right from the standard. This is how the requirements from various standards are worded. This is basically right out of the standard. So, for example, IEC 61010-1, which is the big standard for equipment for measurement, control, and laboratory use. So the way it states the requirement for a high 500 VA test is the generator shall be able to supply a power of at least 500 VA. The test voltage is raised uniformly from 0 volts to the specified value within 5 seconds and held at that value for at least the specified time. Well, there you go. This standard is basically calling for using a 500 VA Hipot tester. So in this case, if you are trying to comply with the standard that's calling for a 500 VA Hipot tester, you have no other choice but to use a 500 VA instrument. Similarly, if you look at the standard at the very bottom, IEC 60335, it's calling out for a voltage of a sinusoidal form having a frequency of 50 to 60 hertz for 1 minute. No breakdown shall occur. Tests run at 4,000 volts or less require 100 milliamp trip limit and a 200 milliamp short circuit. So the 100 milliamp trip limit basically, and if you have a Hipot tester that's capable of 5,000 volts, you have and 100 milliamp output. What you basically have is a 500 VA Hipot tester. There's a few other considerations that that are important to basically know when you're running a 500 VA Hipot test, and it's also very important to understand when is it actually required for you to use a 500 VA transformer, because sometimes the standard will, as we saw in the example, will call out for a 500 VA test, sometimes not, but you have to decide based on your product, how much leakage are you seeing on your products. Based on that, you may or may not need a 500 VA transformer. But unfortunately, a 500 VA output capacity poses a considerable safety risk as well for the test operator, because the higher the current for the Hipot, the more potentially lethal the tests could be. Test operators, they work in an environment that calls for extreme caution, of course, and we've covered all this, all the safety requirements and precautions and safety hazards in some of our previous webinars. So feel free to take a look at them. They're archived on our website. The other thing to know is that it is recommended that the manufacturers do not use a 500 VA transformer unless they are required to do in order to comply with the specification of the test. Again, if you use a 500 VA transformer, of course, if you're required by the standard, or if your product will require a much higher leakage current measurement capability, only then use a 500 VA transformer. If you're not required to use it, do not use it, because there are considerable safety risks to it. A 500 VA Hipot tester is also recommended when testing a product which is highly capacitive, that a typical lower VA rated Hipot will not be able to test the product. So having said that, the other important thing, or a few factors to consider during the 500 VA Hipot tests, are that line and load regulation issues. Well, most there are some Hipot testers out there with the unregulated Hipot output, meaning that if the input voltage to the Hipot test varies or changes, the Hipot tester should be able to maintain the output voltage. This means it should be a regulated output. If the Hipot circuit is too heavily loaded or the input voltage drops, the Hipot test voltage can dip, causing an improper Hipot test. So basically, if you were using an unregulated Hipot tester, what can happen is, if the voltage drops on the input of your Hipot tester, the output will be affected, and you may not be testing at the right voltage, and the test may not be, may be the proper test that you were required to run. On the other hand, a regulated Hipot output is what basically maintains the output, regardless of the changes on the input side. So Hipot testers with a regulated output don't have this issue. A proper feedback circuit is used with voltage monitored on the output, that ensures that the test being performed remains at a constant potential under varying line and load conditions. Now, all associated research Hipot testers are regulated, have a regulated output, and have a feedback circuit that monitors the output and regulates the output if there are variations on the input side. So again, something very important to consider here when using a 500 VA Hipot tester. Okay, so like we just discussed, some standards include exceptions to a 500 VA Hipot requirement. Right out of the standard UL 1598 for luminaries, clause 19.20, these are the words from the standard. If the output of the test equipment is less than 500 VA, the equipment shall include a voltmeter in the output circuit to directly indicate test potential. So here's basically an exception. There are exceptions. There are always exceptions to 500 VA Hipot testing. And what this basically means is that if the output of your tests, if you are not using a 500 VA transformer, then there should be a voltmeter included on the output circuit to directly indicate the test potential. And this is right out of the standard, so something very important. And associated research again makes the instruments that have a voltmeter on the outputs, measuring and displaying the actual voltage being output. So there are there are 5 VA different electronic products. What you can do is that keep your eyes open for new versions of standards, because a lot of times standards get updated, and some extra test requirements may be added or taken out of the standard. So it is very important that you are up to date with any changes that are being made to the standards that you are trying to comply with, or you have been trying to comply with. Again, in the end, you must follow what the standard states. However, if your standard may contain an exception to the 500 rule, make sure you read the standard carefully and understand if a 500 VA Hipot tester is necessary for your testing or not. So real quick, now that we've talked about 500 VA Hipot testing, I'd like to play a quick video of one of our testers. I'm just going to pause it here real quick and What we're seeing here is model Associated Research Model 3780, which is basically a 500 VA dielectric withstand tester. And what's showing on the screen right now is an AC withstand test that's being set to run for 1 second and at a voltage of 1.24 kV with a high limit set to 10 milliamps. So now on the load side, what we have is a pure resistor. As you can see, the high voltage and the return is connected to the appropriate parts on the TVB2 box, which is basically a verification box. And what we see here, the red lead is clipped to a 2 mega ohm load and the black lead to the return. And when we go ahead and press the test button, you can see we're reading a leakage of 0.62 milliamps. Now again, this test may not, this device or load that we were testing may not exhibit such high leakage where a need for a 500 VA transformer comes in, but it was just to show you how a 500 VA Hipot test can be performed on on different types of products. And in this case, it was just a simple resistor. Okay. Next thing, we're gonna again request you to please participate in our first poll for today. We're gonna take a short pause here for a minute, and please, it'll be great if you can participate in this poll. It gives us some really good feedback. And at the end of the poll, Allison is going to announce the poll results to help us, understand how many of you are actually required or are doing the 500 VA test.
Hi everyone, thank you for voting. I'm going to go ahead and close the poll at this time. What we have as results are 44% of you said that yes, you do indeed require 500 VA for your application, as 56% of you, however, said that no, you do not require the 500 VA feature. Thank you guys so much for voting.
All right, thanks a lot, Allison, for sharing the poll results with us, and thank you all for participating in this poll and helping us understand how many of you are actually required to perform the 500 VA. And the answer was 44% of you, as Allison said, are actually performing or are required to perform the 500 VA test, whereas 56% no. And these poll results do make some sense because this is what I was kind of expecting based on this poll. That again, there's 500 VA is a very special application, and not all Hipot tests require the use of 500 VA transformers or Hipot testers. So, okay, great. The next thing that we're going to be covering is we're going to talk about some of the failure detectors that are available in the Hipot testers that you use. The important thing here to know is that all these failure detectors are available to you, and again, we want to make sure you know how to best utilize them and how these failure detectors work. So, starting with breakdown. Now, we learned that breakdown is basically and again, in the previous webinar, I believe Nick did talk about breakdown, but just for our review, a breakdown is a condition where basically a large amount of leakage current is flowing as a result of the high voltage being applied and the insulation being stressed. And it's a condition where very high amounts of leakage current will flow, and the insulation basically was not able to withstand the high voltage application. So that's the breakdown condition. this is a very fast detecting circuit that detects the breakdown condition, almost 400 microseconds interrupt. Then we have the leakage limits. Well, we talked about leakage limits, how we can set the high and low limits. Therefore, leakage limits are also, again, a great way of, checking for Hipot test failures. This is a slightly slower circuit set at 100 milliseconds samples. And lastly, we have arc detection. Again, arc detection, as we've already talked a little bit about, or in quite a bit of detail in the last webinar, but I do plan on, going over it, in somewhat detail during this webinar, as this is, again, one of those topics which is not very well understood, and it's not an exact science, so it takes a while to get the gist of what arc detection really is and what it's doing and how it can be beneficial as an additional feature for your Hipot test. So each failure detector has a priority on the instrument, meaning that the shorts and breakdowns will always be detected with a high-speed interrupt. Leakage limits will trigger a failure if leakage current strays from the user set values, again, are high and low limits. Arc detection is the extra feature which can be enabled or disabled depending on what the user or manufacturer is trying to understand. If you want extra information about your product installation, arc detection is a good feature to use. But again, arc detection is not exact science, so the results may vary, and depending on many different factors. Here's a quick picture of how the actual circuit is designed to detect these different types of failures. So as you can see on the top, we have the high voltage transformer of our Hipot tester, and applying the high voltage to the DUT, device under test, and the return circuit, measuring the leakage current. So we're going to start with the very bottom, which is the overload condition, which is basically the high-speed breakdown and short that we talked about. It's a high-speed circuit, and it basically detects a shorting condition or a breakdown condition at very high speeds. So this takes priority over the high and low limits. Next, we have the leakage meter. Basically, these are 100 millisecond samples based on our high and low limit that we have set. Programmed in our Hipot tester for the Hipot test. And lastly, we have the arc detection, which is again a high-speed interrupt, and will trip right away and takes priority over the leakage meter detection. So now that we've talked a little bit about some of the failure detectors and different types of failures that can occur during the Hipot test, we're ready to look at a couple of videos, and the one that I want to show you first is the breakdown failure video. And in this test, basically, I'm going to pause there. What we have is, again, a AC withstand test set at 5,000 volts for 5 seconds with a high limit of 50 milliamps. And what we're going to do is we're basically, we have the high voltage and the return lead very close to each other with the very small air gap between them. And since air is also a dielectric, I'm just going to play this real quick again while I talk about it. Air is also a dielectric. A breakdown can occur within the air. And that's exactly what happened here. At a 5,000 volts, we saw some breakdown occurring through the air, and the instrument instantly catching the breakdown failure. Okay, so that was our breakdown video. The next one that I want to show you is we already looked at the high limit failure. Yeah. So what we have here is, again, a capacitor set to be tested at 5,000 volts again, and the failure occurs based on the high limit that we had set. So this is different from it's a slower detection circuit, and it's based off of the high limit that we set. So next thing, we're, like I said, arc detection. I would like to cover arc detection a little more in this webinar. It's been covered in quite a bit of detail in the last webinar, but just a quick, review of arc detection, since we had quite a few questions on this feature or a function. Basically, the way our arc detection works is that high impedance arcs and corona generate high frequency current pulses that ride on the low frequency wave of the applied test current waveform. So on the left, you can see those high impedance arcs riding on the low frequency test current waveforms. What happens is the way arc detection circuit works is that this passes through a high pass filter, which basically filters out the high impedance arcs. Next, most of our Hipot testers have the arc sensitivity level adjustment that is user adjustable. So basically, you can go ahead and program an arc failure condition based on those numbers from 1 to 9. And what then happens is, once those high frequency arcs are filtered, they're compared with the user sensitivity level. And if the high frequency arcs are compared to be at the user sensitivity level, the CPU gets an interrupt, and within 400 microseconds, and the instrument will display the arc failure. So based on the user sensitivity level that you have available on most of our arc detection, on most of our Hipot testers for arc detection, 1 being the most, the highest, which corresponds to 20 milliamp trip level, and 9 being the lowest, the most sensitive, at 2 milliamps. But it is important to remember that this method of arc detection is not an exact science. There are many variables involved, including surface geometry, altitude, atmospheric pressure, and other environmental factors that can, affect the arc detection readings or failures significantly. So it is very important to know that this is not exact science, and that is why there are hardly any standards that call out for measuring for arcing. So now that we kind of reviewed what arc detection is, we are ready to look at a quick video which is showing arc failure. What we have here again is a 5,000 volts AC withstand test with arc detection set to on, and what we have here is basically a piece of mylar. And what I know is that if it wouldn't break down, but there will be some surface tracking, and you can actually, when I ran this test and recorded the video, you could actually hear some buzzing going on, which is an indication that arcing may be going on here. So when we perform the test, as you can see, the voltage ramps up towards the 5 kV value, and during the dwell cycle, the instrument comes up with the arc failure. So again, this is a high-speed interrupt, and due to the thin mylar film that was between the high voltage and the return leads, caused some surface tracking, and as a result, there was arcing going on, which was detected by the instrument. And having said that, we're now ready to have you participate in our next poll question, which should be up shortly, and we'll take a quick minute break here, a pause, and we'll highly encourage you to participate in this poll.
All right, hello everyone again. I am going to close the poll. Thank you all for voting. An overwhelming amount of people, 71%, said that warning signs and safety interlock DUT enclosures at 56% were used as safety features, as well as signal tower lights at 39%, e-stops at 37%, and SmartGFI feature at 32%.
All right, thanks a lot, Alison, once again for sharing those results with us. And it's based on the results that we saw from the polling, it seems like a lot of you are utilizing most of these safety features and other functional features of your Hipot test instruments. So that's great to know that you guys are aware of those features and are utilizing those to the best of their ability. So that's great to know. And having said that, we're gonna do is talk a little bit more about some of the Hipot instrument features, such as starting with the safety features, SmartGFI, Interlock. Well, all our associated research Hipot testers do utilize these two basic safety features. The SmartGFI, basically, it's there to protect the user from electric shock, meaning that if by mistake the user gets in touch with the DUT that's being tested, that's being charged up during a Hipot test, and if any current flows through the operator, the SmartGFI circuit will detect that the current returning, on the return line is not matching up with what was, basically used during charging up the product. So it will trip right away and protect the user from being electrocuted. Same goes for the interlock. The interlock is a interlock disabled key that is used with all of our Hipot testers, and without this key, the instrument will not output any high voltage. And if the interlock key or if the interlock is disabled during the Hipot test, the instrument will instantly stop the output or abort the output. And we're going to talk about these two features a little bit more in detail. But the next thing we want to talk about is safety and other safety and functional features such as prompt and hold, and some other features like ramp high and charge low. One thing to note here is that all associated research instruments have a variety of built-in features to ensure that the operator safety and streamline testing. So we want to make sure, we want to educate you to understand that the Hipot testers and other electrical safety testers that you are using are capable of very potentially hazardous amounts of voltage and currents. So we want to make sure you understand the all the safety hazards associated with Hipot testing and the precautions that you need to take when using our instruments. And it's all, again, comes down to the operator safety. So the way SmartGFI works is that it can detect when an operator is touching the device under test by monitoring the leakage current, as I said before. Standard units have a trip setting of about 450 microamps, at which so basically if the SmartGFI circuit detects a deficiency of 450 microamps between the high voltage output and the return, it will trip and stop the output. It kind of knows that something's not right, and the amount of current that was outputted is not returning back through the the return line. Whereas some of our more advanced and all-in-one analyzers have a variable range, basically a range of current that can be set by the user, starting from 400 microamps to up to 5 milliamps. And these instruments include Omnia 2 series and the new Hipot Ultra. Again, the SmartGFI on these instruments is user adjustable. The user can actually go in and set a value and program the instrument to trip if it sees this much current for, deficiency during the Hipot test. Next, the interlock. Well, the interlock is basically, is the way we use our interlock is we have what we call the interlock key, which is located. Which what it does is it shorts pins 4 and 5 of the signal or remote input of our Hipot testers. Now, the way interlock works is that it can be used with a variety of different applications, meaning that it can be used, it can be used to wire to a DUT enclosure, meaning that if, for a safe workstation, you want to keep your device under test inside a safety enclosure, so to prevent any, accidents or anybody getting in touch with your product under test, because it's charged up during a Hipot test, and touching it can cause an electrical shock to whoever comes in contact with it. So our interlock can be interfaced to work with our safety enclosure, meaning that it can be hardwired to the enclosure, and as long as the enclosure door is closed, the interlock is available. As soon as the enclosure door opens, the interlock breaks, and it basically aborts the high voltage output instantly. And it can be wired to the DUT enclosure for an extra means of operator safety. Again, this picture is from one of our older, first few webinars that we for this year on basics of electrical safety testing, setting up a safe workstation, and it's showing other good techniques to set up a safe workstation, and using other important safety equipment such as the high voltage sign, the e-stop switch, the signal tower light, and the high voltage mat. The next thing is prompt and hold. Well, this is a feature, on some of our high-end electrical safety analyzers. And the way this works is that it allows the user to set instructions during the sequence. So in this picture, as you can see, that you're at this is again an screenshot of the Omnia 2 analyzer, and as you can see, we're looking at the perform test screen, and what we see is a bunch of different test steps, starting with a DC withstand, ground bond, AC withstand, IR. Again, a ground bond test, a continuity test, so an entire test sequence with multiple test steps. What the prompt and hold feature allows the user to do is that you can add visual, audio, and visual prompts, also videos in some cases, and it allows the user to set instructions during the sequence. So when the first test step is over, a prompt message such as shown on this screen will occur, and on that prompt, you can basically program any text or instructions or videos to, to give some good information to the operator running the test, and to instruct the operator to make the necessary changes to the device under test. And during this period, when the prompt and hold feature, what it does is it does not, there's no output, the instrument is not outputting any high voltage, high current, or whatever, depending on the type of test you're running. And it will, the user set prompt will hold the sequence until the operator presses the test button again. So this could be used to convey a work instructions for safety purpose. Again, a great feature to have if you're trying to perform your test in a safe manner. Other last few things. I know we're almost to the end of our 1 hour period, allotted period of time, but a couple of more things that I want to throw out there. I know we've already talked in quite a bit detail about AC versus DC Hipot tests, and today's webinar was mostly based on AC, because 500 VA requirement comes for an AC Hipot test only. For the DC Hipot tests, I want to make sure there's a few things that you guys are aware of. At the test start, there will be inrush current, because due to the very nature of DC potential, once the insulation is charged to the full test potential, the leakage current drops off to near 0 amps. Well, the two features that we have available for our DC Hipot test are ramp high and charge low. The way these features work are, first starting with ramp high, what this feature does is that it will ignore the inrush current values, so the DC Hipot does not falsely fail. Meaning that when you perform a DC Hipot test on your device, the ramp high current will ignore the inrush values and will not fail based on the high limit and that you have set, and it will allow the high inrush current because you don't want to because that's the inrush value, and that's not what you're looking at. You're looking at the the leakage value. So it avoids or it prevents a false failure during a DC Hipot test. Charge low, where for the DC Hipot test, is a great feature to have. Basically, at times it's actually better to use charged low instead of a low limit for the DC Hipot test, because what happens is that when you run a DC Hipot test, the charged low monitors the Hipot circuit with the device and the test attached. Then, when the test is run, the charged low circuit takes half that inrush current value and substitutes as a low limit check. What this tells the user is that if some of the test leads or any test lead or connections are not made properly, you will see a charged low failure. This is a great indication to you that somewhere in your connections you missed something, or you need to go and check back your connections. So these features are used with a DC Hipot or an insulation resistance test, which is basically a lower voltage DC Hipot test. And now, due to the nature of a DC withstand test setting, DC withstand test, setting high and low leakage limits can prove difficult, because we know DC potential works much differently than the AC potential. These features compensate for this difficulty and allow the user to properly monitor the high and low limits. So again, great features to have, and if you do have these features and you are running if you are running a DC Hipot test, and if you have an instrument that has these features, I would definitely recommend that you utilize these features, as these are great. These will help you a great deal in performing your Hipot test properly, and recording all the failures properly and the way it should be done. So that kind of concludes our presentation for today. Once again, I would first like to thank you all for being patient and joining us today for this very important webinar during our 2015 series of webinars. Once again, today we covered a lot of special applications for Hipot testing, and on this screen you can see, if you would like to obtain a copy of this presentation, you can contact Jim Kennedy, jimk@asresearch.com. We have our website, asresearch.com. You can follow us on YouTube, LinkedIn, and Twitter, and all the web addresses are located on the screen. And at this point, I would like to leave the forum open for any last-minute questions that you have. And again, if there's something that gets unanswered, feel free to email Jim with your questions, and Jim will be forwarding all those questions to me, and I will definitely reach out to you guys to address any concerns or questions that you have on this presentation, or on any other topic related to our instruments or safety testing. Okay, I guess I don't see any questions on the chat line yet. And Allison, can you please confirm if anybody had a question that I need to address at this point? Or
Actually, Syed, it does appear that we do have a question. It's how do you calculate theoretical flow?
how do you calculate theoretical flow?
Yes.
Okay. Not sure exactly what that means. Maybe it's a different term for something that we name differently. So if you can elaborate, whoever asked this question, can you elaborate a little bit on what exactly are you asking? What do you mean by theoretical flow?
And while we wait for that, I have another question. Do you have a similar one for ESD?
So ESD, electrostatic discharge. Well, and similar what? Like in this, a similar presentation or a similar? I guess the question is kind of incomplete here.
Okay, and then our last question is there any direct relation between the actual leakage current measured by the leakage tester and the total current measured during Hipot tests?
Yes, so like we saw and like I discussed, most of our Hipot testers are able to distinguish between the real and the imaginary leakage. Therefore, first of all, it is important to understand the product that you're testing. What kind of, is it a highly capacitive product, or is it more resistive, or is it purely resistive? Usually the case is it's mostly capacitive, slightly resistive, and most of our instruments or some of our instruments can determine or distinguish between the two. And it basically depends on the manufacturer if what they're looking at, if indeed they want to look at the real portion of their current as well as the total. Okay, I guess at this point we have no other questions. Once again, I'd like to thank you all for taking time out to join us today. And our webinar schedule is up on our website. Our next webinar is Electrical Safety Testing 201 on June 10th, 2015 at 10 a.m. So hopefully all of you will join us for that very important webinar. This is your host, Syed Abidi, signing off, and a big thank to you all again, and to Bishan and Allison for making this webinar a success today.